Dear colleagues, today is our seminar and our guest, Professor Davide Bonifazi. He graduated with honors from the University of Parma, Italy, where he received a degree in industrial chemistry. In 2004, he defended his PhD thesis at ETH Zurich, Switzerland. Afterwards, he worked as a postdoc, first in the group of Professor François Diderich in ETH Zurich in Switzerland, and then at the University of Trieste in Italy, under the supervision of Professor Maurizio Prato. Between 2006 and 2012, he was a junior professor of organic chemistry at the University of Namur in Belgium. Additionally, from 2009 to 2016, he held a part-time position as an associate professor of organic chemistry at the University of Trieste in Italy. From 2012 to 2015, he held the position of professor of organic chemistry and was the first fellow member of the Namur Research College at Namur University. Then he spent 5 years as a chair professor in organic supramolecular chemistry at the University of Cardiff, United Kingdom. And since April 2020 and up to now, he has held the position of chair professor in organic chemistry at the Institute of Organic Chemistry, University of Vienna, Austria. Starting from 2020, he has taken on the role of associate editor for chemical communication at the Royal Society of Chemistry. His research interests focus on the design and development of synthetic strategies for preparation of organic molecular structure that can contribute to demonstrating key functions of basic concepts in highly interdisciplinary fields and frontiers between organic chemistry, physics, material science, and recently biology. Current topics include 4 research areas: supramolecular organic nanochemistry, advanced materials based on carbon nanostructures, multifunctional photoactive pi-conjugated architectures, and supramolecular chemistry interfacing cellular function. And here, Davide, please, you can start your lecture.
So, hello, everybody. Do you hear me? Yes.
Yes.
Good. So first of all, I would like to thank Olesia and Valentine for the invitation to give this seminar today in your contest, and just only want also to express all my solidarity to the situation that you all are experiencing during this very hard time. So in this 45 minutes of today's talks, what I'm going to show you, it is a glimpse of our research activity. And in particular, today, what I'm going to focus, it is on the field of molecular graphenoids and the synthetic strategy and their use in some application. So, our inspiration, we are organic chemists. And then as all the organic chemists, the inspiration, it is to prepare a molecule, to prepare a material, so to prepare a natural product. In our case, the inspiration has been always the graphene. And the graphene, why? It's not really to synthesize a graphene. It is just only because on the graphene, you can build a whole series of different molecular structures, which has different properties depending on the size, depending on the peripheries, depending whether it is monodimensional or bidimensional. You can get this armchair, you can get this zigzag. And so you can have a really large variety of molecules, of which the property of which can be tailored with the extension, the peripheries, and then with the arrangement, the different arrangement of the sp2 carbons. Why those are interesting for us? Those are interesting for us because by changing the properties, we can change the homolumo gap of this molecule. And so essentially, we are semiconductors. And these semiconductors can be used in some application, in some optoelectronics, which can then have some real application. For example, all these organic materials could be used, for example, in these different type of applications that can go from liquid crystal to LEDs, electronic papers, electrochromic devices, and you name it. So when you look at this whole application, it clearly shows you the potential of this organic. And for the organic, what we can see in general for semiconductors, it is that the projected global semiconductor market for the 2023, so last year, it was around 550 billion US. And the organic section was around 60 billion US dollars, which tells you how much room we have for the application of this type of molecules. Now, if you can imagine now that with the organic, we try to replace all the inorganic with the organic, then we could target a huge portfolio of application with a lot of economic impact. The problem it is what? That when you have these organic materials, it is that you are not depending on to the natural resources, because usually all the semiconductor depends on inorganic resources. For example, based on rare metals, based on natural resources. When instead, if you think that you could replace the inorganic with the organic, so the organic, you could prepare them everywhere. So you are independent on the local natural resources. You can prepare them everywhere. The problem of having only the organic, it is related to the intrinsic properties of these inorganic materials, which are the light and thermal sensitiveness, because of course they tend to degrade. Something inorganic, they don't do it. And then they are prone to oxidation and then to reduction. And so when you do multiple cycle of this oxidation, reduction, they tend to decompose. And then another problem, it is more on the engineering part, that is difficult sometimes to control in a reproducible manner all the solid state organic. But okay, it is a secondary problem. The first problem, it is you get an organic, and then the organic tends to decompose. And so the first story I would like to show you, it is how we can make this molecule stable. And so one of the ideas would be, you get an organic molecule and then you put in a ceramic. So what does it mean in a ceramization? In a ceramic, so essentially you cover the organic structure with a kind of a ceramic, for example, a boron nitride. And this is what I'm going to show you. So if you take a slab of graphene, then how can you dope the graphene? How could you change the graphene? You could change it, for example, the structure of the graphene, by integrating something that has more or less the same structure. And then what is among all the possible graphene-like structure that has a similar structure? It is the boron nitride. If you now take the boron nitride, which is a complete insulator, then you see that the structure is the same, is also hexagonal. So we could replace the carbon-carbon with the BN bond. And then you could exploit the isoelectronic properties, the fact that they are highly polarizable, and then the fact that you introduce a very stiff material, stiff bond, into something that is carbon-carbon. And so you put it a kind of ceramic inside of an organic structures. And so this will help on the stability, because as you know, BN, boron nitride, are ceramic, which are used as a very strong materials against oxidation, against abrasion, against mechanical stress, against oxidation. So they are really, is a ceramic, it's really strong. Now, the things that you can do it, not only to make it the molecule more stronger, let's say less sensitive towards decomposition, towards chemical reaction, but also since it's insulating, what you could do, it is that if you blend the two in molecules and you try then to add the BN localized in different positions inside of this graphenoid type structure, you would be able to tune also the optoelectronic properties, which means you, from a graphene that is a metal, you could create a semiconductor, and the property of which would depend on the amount of BN that you add, on the position of this ring, if it is peripheral, if it is central. So this is our whole possibility that we could use, and then eventually it could open to an infinity an infinite number of materials with different properties, both chemicals and optoelectronic. The problem it is what? How can we introduce this BN? So here we have a synthetic challenge. Because when you talk about the boron, nitrogen, and carbon, and in particular boron, nitrogen has, from the chemical point of view, completely different properties. Boron, it is electrophilic. Nitrogen, it is nucleophilic. One resists to oxidation, the other one resists to reduction. And so what happens that the number of possible type of reaction that we can do with this type of molecules is quite narrow. And so, again, I don't want to do any graphene, any materials here. We restrict on the molecular level. And so the strategy to add this BN in a carbon-carbon scaffold would be, the first one possibility, it is that you pre-organize the carbon, and then you add the boron nitride. For example, you add amino groups on your carbon structures, and then you borylate, and then you place the boron next by to the nitrogen. Another possibility would be that you put also the nitrogen in the structure, and then you fill it with the boron through, again, borylation. So this is basically, you create first the carbon framework, and then you add the boron. A second would be that you do first the BN, and then you do an annulation reaction. So for example, here, before you create your BN, and then you find a way to do a carbon-carbon bond, which then can then form all the graphene type structure around the BN. Okay, so those are the two strategies that one can use. So now let's start with the first strategy, which is pre-organization and then addition of the boron at the last step. So at the beginning, we focus on synthesizing this type of molecules, which are peri-acinoacenes. Here the periphery are all zigzag, so it is very reactive. And so usually they are unstable under oxygen condition because they tend to oxidize in all these positions, forming the quinoidal structures. And so the idea, it was the following, to try to prepare this molecule. So this would be the structure where we add this NBN in this position, in these peripheries. And the idea would be, first of all, we create a oligomer of benzene, phenylines, which bears the nitrogen, and then with the nitrogen, which are protected, then you protect the nitrogen, then you go with the borylation reaction, which then should fill all the gaps with boron directed by the nitrogen. And so this is what we did. So we prepare a series of these polyphenylines, aminated polyphenylines derivatives. So I skipped the synthesis of those, but those has been made by a combination of Suzuki coupling and Buchwald-Hartwig relation reaction to install this substituent on the nitrogen, which are mesetyl substituent, to give solubility, because otherwise these molecules are really unsolved. And then the idea, it was then to introduce the boron. And so what we did was the borylation reaction. So this borylation reaction with BPR3, we also got inspiration from literature that did similar stuff but on a smaller system, or not on nanoribbons, for example, to do the NBN. And so then we added the borylate, we added the BPR3, we boil it, and so then you quench the reaction with an organolithium to go and to add a substituent on the boron. And so for the small term, we got in one step a 3 borylation. And so in this case, what we did 3 plus 2, 2. So we did in total 7 bond with a good yield. Then we go with the tetra. We did the same things, but we had to increase the temperature. You see, we went from 170 to 230. Again, in one step, 4 boron, which have been installed. Then we did the same with the 5. Then we did the same with the 6. As you can see here, when you increase the length of your meta oligophenylines derivative, we need to increase also the temperature, and this is due to not really due to the fact that the molecule becomes less reactive, because it is the opposite. Here the molecules, as you start to planarize and elongate the structure, they become more reactive, because the HOMO of the nanoribbons rise in energy. It is rather than when you added the BBr3 at the beginning, the BBr3 form Lewis acid adduct with the anilines, with the nitrogen, the basic nitrogen, and makes really a very insoluble salt type, which need to have a high temperature to be redissolved. And so this is what we had. So to get the synthesis of the longest system, so what we had to do, it was to increase the temperature very high to around 330 degrees. So how to determine the structure of this molecule? So we had to use the X-ray, and where we show exactly the positioning of the boron in the different nanoribbons in the position that it was expected following the borylation reaction. So as you can see here, so the molecules that we got the crystal up to the 5, they are all practically almost flat, as you can see here, with a little distortion of the mesotype, which anyway give enough solubility to do the characterization. Okay, so this was one thing. Then what we wanted to try to do, it is, let's see if we can expand the family by fusing other aromatic rings. And so this is what we move. So instead to elongate, we added another polyaromatic hydrocarbons, which is this perilene. And then we try to do the fusing of this perilene with the same reaction. And so again, BBr3, then you quench with the organolithium, and then what you get here, again, the installment of the 3 boron, only that here you see that we did also a boron-carbon bond to an additional boron-carbon bond with a pretty decent yield. Now, how we did again the X-ray structure to show that the boron, it is installed in the right position. And this is just only to give you a glimpse of the properties. So here you see that we create a molecule that is really highly fluorescent. We have around 90% of fluorescent quantum yield, and with a lifetime typical of a fluorescence, which is around the nanosecond. So these molecules are really, really fluorescent. So we took this molecule, and also we put, which I don't talk today, but we will put also on a device, and in particular, this has been done in collaboration with a group of Ruben Costa at the TUM in Munich, in which we create legs, and then what we show that this molecule in legs, they show really high resistance, and so the legs can work for days without having degradation. And this is when it is compared to the full analog, so with only carbon, that one decomposes after a few hours, which then shows ultimately our idea of adding this BN and to make the molecule more robust. Then what we wanted to do, it is to see whether we could increase further the expansion with this pyrene. And so then we prepare molecules. Again, this is always a combination of Suzuki and Buchwald-Hartwig relation reactions. And so we build this dye-substituted pyrene derivative. And then we did the borylation and again, addition of the Grignard. And then we got this molecule that we could not really characterize because the molecule turned out to be really, really insoluble. So this was started to have some limitation. And it was a problem if we wanted to extend. So Marco worked hard to try to get a different isomers. So instead of putting in these two positions, in this pseudo transposition, we put in this other position on the perilene, and then we did again the borylation. We got this molecule, and this molecule at least we could partially work with, and so it could be at least workable. So we got the characterization with the mass, but most importantly, we got the crystal structure. So you see here what and how the molecule look like. So we have what we thought, where we have the NBN here bridging the two arms of this molecule, and then the lateral BN here, and then here the boron, where it makes the two carbon one carbon, one bond with this with the pyrene structure, and the other one with the benzene. Now, when we look the molecule closer, so you see that this part is mainly planar, but when we look at this part, so where there is the pyrene, it is a little bit bended, and so what we suspect that there is a movement of the like a tongue of this functional moiety of the pyrene, which goes up and down, which then creates some distortion in the molecule, as you can see here. Okay, so this molecule turned out to be okay in terms of solubility. So then we could characterize. So here you have the characterization. So you see that is the molecule this time, it absorbs almost all across the UV visible. And so the color of the molecule, it is a deep red. It's kind of blood red, which has also this emission. And the emission is around, as in terms of quantum mean, around 80%. And then it is also a moderate good singlet oxygen sensitizer. So which means that this molecule has both populated the singlet and the triplet excited states. So we probe also this molecule in LEX, and then again, they observe some emission from the device, which was good. Good. Now, to try to overcome the solubility problem, because all these molecules, they are kind of their, one of the main problems, what I told you, it is the solubility. We try to see whether we could also create molecules in which the boron, it is not anymore a boron that is planar, so it's a trigonal boron, but it becomes tetrahedral boron. And so one way to do it would have been to add, instead of one pyrene, to put two pyrene and add a pyridine here. When you do this, again, with this normal Suzuki and Buchwald-Hartwig cross-coupling, and then you do the borylation, so again, BBr3, and then you quench with a phenyl magnesium with a Grignard. So in this case, the boron, you insert the boron here, but this boron is linked to a pyridinium, if you want. This boron is extremely electrophilic. And so a molecule of organolithium could add also on the central boron to make this boron tetrahedral. And so essentially you add a functional group in the middle that should allow a better solubility. And this is how it looks like the molecule. You see there we got these very nice red crystals, and it is the crystal structure. As you can see now, the molecule is not anymore planar. You have this boron that is tetrahedral with a phenyl pointing up, and then now this molecule becomes very soluble. And also because you can see here, there is not this full planarity, so it kind of analyzing, it resembles the structure of analyzing, although here the energy barrier is very low, so then we could not separate the two enantiomers. And it is what we got. And again, the molecule, this is really pink. So the quantum yield, we are around 90% in terms of quantum yield of the singlet emission. And again, this molecule now, it is very easy to be processed because it is very solid. So now, since we have now this new method to try to install this tetrahedral boron in the middle of the molecule and to make it more soluble, then we could expand the system and then to try to get more extended system. And so if now you start with this molecule, so we take this pyridine, which bear one iodine and one bromide. So I don't report the synthesis of this, but this is where already 3-4 steps of synthesis. And now then you add one pyrene, so you can selectively react at the Suzuki at room temp at iodine and the bromine in different conditions. So you add one lateral pyrene here, and then you create this pyrene pyridine. And then what you do a reaction, a double Suzuki on this bifunctionalized pyrene with two boron, and then you get this tetramer. And then now, once you get this tetramer, you do the borylation, again, BBr3 and Grignard. So what you end up with this molecule, that is extended, in which you have two boron, okay, this time, which bear the both boron to phenyl. And then these two phenyl are attached on the boron, and they are perpendicular with respect to the plane, if you want, of the molecule. So the color of this molecule, again, it is intense red, not violet, it emits in the red. But this molecule, as you can imagine, it is made of two different isomers. The isomer in which you have the two phenyl on the same side, and the isomer in which you have the phenyl on the opposite side. And this is because we could not control so far the addition of the two phenyl. So when you add the Grignard at the end, so basically you get 1 and 1 on the one side, but also could react with the same statistic to the other side. And so essentially we could get two different diastereoisomers. And we got preliminary X-ray. So this is the cis isomers. So in which, and it should be the meso. And so here what you get, it is the two phenyl which are pointing on the same side. And then what you get, the trans isomer, in which the phenyl are pointing on the opposite side, okay? And this is, of course, you can get the two enantiomers, and these are the two mirror images of the trans, because the trans, it is chiral. Something that we should consider, that also the cis could be chiral, but since here the inversion, because this is kind that you have allicins, but since here you have an inversion of the allicins, so essentially all the molecules, basically the chirality of the molecule comes from the tetrahedral boron, okay? Because you have an inversion. Okay, and so then I could show, and these molecules again are quite soluble because you have this boron. And so now what we are doing, we are trying to study this, the photophysical properties of this molecule, and then to see whether also we could, because we did not do yet the separation of the chiral molecules, and so of the two enantiomers, and to see whether we have a strong circular polarized luminescence, that it would be good to engineer devices that emit polarized light. Okay, so this is it. So this is just show you a couple of examples of what we can do with the first approach, namely before we build the carbon-nitrogen structure and then we insert the bond. What about the second strategy, which is what I told you? It is instead before you prepare the BN and then you do the carbon-carbon. Now let's go just only to make a summary of how you can prepare a carbon-carbon bond to prepare in general molecular graphenoid. So one of the possible reaction, it is the one that has been the most used by Klaus Mullen and by many other people, it is the Scholl reaction. So essentially what you do, you take your phenyl and then you add an oxidant, and then under the oxidation you form a pi-cation, which this pi-cation undergo addition, reaction from a non-oxidized phenyl, and then you make the bond, and then elimination of a proton, then you get the carbon-carbon. Another way, it is a photochemical cyclization, so it's a Mallory type reaction in which by irradiation, you undergo with electrocyclization, and then if you have an halogen, then basically by adding a base, then you can get an elimination, and then essentially you get aromatization again. Another possibility instead is metal catalyzed, so you put a metal and then you, through CH activation, you can form the carbon-carbon bond. And another possibility, it is to create highly reactive species on the carbon. And these highly reactive species could be, for example, a carbocation, an sp2 carbocation, or a radical carbocation. And so these two approaches could allow the formation or equal formation of this carbon-carbon. What is the advantage eventually of using this compared to the previous? It is that the Scholl reaction usually it is, when you use iron, it is sometimes incompatible with some functional groups. And you cannot do it when you have electron withdrawing groups. The Mallory type reaction, of course, are highly dependent on the substituent because it depends on how efficient you can get this electrocyclization. The meta-catalyze, of course, you need to put some activating group, but also, again, it depends on the steric requirement. If it's sterically too demanding, then it could not happen. And then also you need to rely on precious metal. While here, you can, in these two cases, the reactive species that you can form, it is very small, localized, so usually does not go around, so you don't get side regioselectivity, and you could, and it is very reactive, it's very localized, and so then it does not feel so much the steric requirement. And so this is what we use it. So in an early work, this is already a few years back, but was to prove the concept. It is that this BN, they could not be synthesized with the classical Scholl type, palladium or Mallory, but only with the electrophilic aromatic substitution. And this was our example, in which we prepare this first, borazinocoronine through a first rational synthesis in solution. So essentially what you do, you take a silyl cation, so you use this fluorinated aromatic rings, you go and you basically you do an electrophilic aromatic substitution thanks to the fact that silicon cation coordinate the fluorine, and then this is depart, leaving a type of aryl cation, which then undergo electrophilic aromatic substitution. So we use this reaction that has been developed by J. Siegel around the 2000 to do this carbon-carbon bond. And then what we could prove that we could prepare these molecules and make 6 carbon-carbon bonds. You see that the yield was not too great. We got only 5% of the total molecule, which correspond around to 70% per bond. I just want to remind you that this molecule was also prepared one year earlier than us, but it was only with flash pyrolysis, and then they could not characterize the optoelectronic properties. Equally, we could do and optimize the procedure when we place the fluorine on all the phenyl ring, and then again using the same silyl cation approach to prepare again the borazines, and then we could improve the yield around 50%. Now, when we do everything in the glove box, so we could achieve around 25–30% yield, which is, of course, quite good. The only problem of this procedure, it is that you need to prepare this silyl cation a strong electrophile, it is not the easiest procedure, and of course require that you work under strict water-free conditions. And then, as I told you, when we work in the glove box, we could get 30%. So it means that you need the glove box to get even higher yield. So that's why what we wanted to do, it is to try to explore a different approach. And this different approach would have been with the carbon radical, with the aryl radical, which are equally strong reactive species. And so the idea here started to work with the PIC6. It is a molecule that we use in the laboratories that we investigated for also optoelectronic properties. But the PIC6, what is also a group properties of the PIC6 is that it can be used as a good photocatalyst to do photoreduction and then to form a radical species that I'm going to talk to you in a few minutes. And so here, the idea was to use this PIC6 that has a very good quantum yield for the singlet, around 60%, I mean, good quantum yield, and then to use it in the photocatalytic cyclization reaction. And so this is the molecule that we use as a reference. to explore, to see whether we could form the carbon-carbon bond. And so if you take PIC6, you put the D pair. I'm going to show you after the mechanism. And then we could observe that we could do the carbon-carbon bond under quite mild condition. And so we did some optimization, and when we figured it out, then when we are in the MSO with around 2% of PIC6, you see very a small amount, we could get this molecule in 75–70% yield. And so, and this first reaction was first developed by a former student in our group, Olivia. And then when we move to Vienna, then another student, Davide, took over our project, and then we finished all the investigation. And then at the end, we could see that we could couple and we could make a lot of carbon-carbon bond, also with different species that are not only benzene. So just only to give you a glimpse, so we could cyclize derivative in which there is the substituent in different position. You see in para with respect to the carbon-carbon or to the ortho or to the meta. We could put 2 electron withdrawing group. So another system, we could functionalize it with a system in which they bear electron donating groups, these 2 methoxy, these are dianilino, a pyrrole, a tersbutyl. And we could also fuse, for example, polycyclic aromatics, the pyrene. We could fuse the anthracene. We could make also 2 carbon-carbon bond with a pyrene or with this aniline. And so the method revealed to be quite versatile. So versatile, and then we wanted to see whether we could use also with the boron nitrogen, because in this case, we operate at very mild condition. And then what Davide did, prepare a couple of substrates in which we have a BN bond, and then try to see whether we could do this bond, carbon-carbon bond. And then actually we could. So if you take a cyano or you take an ester, we could make the carbon-carbon bond. We could also move the cyano other position, and again, the reaction was quite profitable. And then we could also make 2 carbon-carbon bonds in the presence of 2 BN. And then this system showed to be quite versatile also in the presence of heteroatom due to the fact that it is quite mild. So now, how does it work, this mechanism of this reaction? So this is essentially, it is a photocatalytic system in which the PIC6 acts as a photocatalyst. The mechanism, it goes through a photo-oxidation of the PIC6. So essentially what you take the PIC6, you excite the PIC6 at a singlet. So we observe that it's the singlet, not the triplet, that is involved in the mechanism of the carbon-carbon bond formation. And then what you get a single electron transfer. So you form in the first stage a pi radical anion. The pi radical anion undergo that dissociation, and so this dissociative elimination of the chloride. And so the chloride leave as a Cl-, and you leave the radical in this position. And so then the radical then undergo addition with the neighboring phenyl. You form this radical intermediate, which then could be reoxidized by the oxidized P cation to give you the PIC6, the initial PIC6, and then this undergo a proton elimination, and then you get the final carbon-carbon bond. What one also could consider that this radical intermediate that is very reactive could be also the source of reduction of the initial cyanochloro derivative. So which could also lead to a chain type radical mechanism. So this is, we cannot exclude because we did not measure the absolute quantum yield of the reaction. But what is very important for us, it is that this system proved to be versatile also for the boron nitrogen. And now why? Because as I told you at the beginning, you form this radical, but this radical, since it sits on the sp2 carbon and is not delocalized on the pi, as, for example, when you do a Scholl reaction, you create a pi cation. And the pi cation, that is delocalized everywhere. So if there are other groups in different positions which could interfere with the pi radical cation, then it does, and then it kills the reactivity of the pi cation. while in this case, the radical is persistent, located in one position. And then, even if you have heteroatom here, this radical has a minor effect on the, the heteroatom has a minor effect on this radical, and so then it can react even in the presence of this system. And so it is the reason why this type of reactivities then become compatible with heteroatom. Okay, so now what we are trying to do, it is to develop a similar system, but that can work also with a system that do not have cyano group and essentially are naked with no substituent, and to see whether we could substitute to give a complementary tool to the Scholl reaction, which also could work with non-substituted full carbon system. And this is what we are currently doing this month, and hopefully I will be able to talk about that in the next months. So now, to conclude my talk, I want to show now another system in which we could essentially, another system in which we use these properties of doped materials to do some function. And the idea here, it is to introduce some dynamic functionality on a pi aromatic system through the heteroatom doping. And this time we move from BN to oxygen doping. But now before to discuss on the topic, on the molecules that we prepare, show you the idea that we wanted to do. Now, let's imagine that you want to use molecules to prepare, for example, materials for information encoding. So what you need to do, it is molecules that can be used to store some information. And how do you store the information? Usually by changing the structure of the molecule upon a stimulus. For example, molecular switch. Molecular switch developed by Manis in the field of molecular switch chemistry. So basically what you do, you get, for example, the azobenzene, that you go from one configuration trans, you move to the cis, and then to the trans and the cis, different properties as associated. And so then we can use the trans and cis to encode an information which could be a 0-1. So, you know, all our information encoding system is based on a binary system. It's a molecule that can have two different states, can encode a 0 or a 1. And this has been always one of the main applications of this molecular switch. Now, what we could also consider, it is to do a chemical reaction that is dynamic. So a chemical reaction, you react A with B, then you form an adduct that is C, that has different properties that is constituent. But then this dynamicity should be also reversible, because then if you want to erase the information, or you want to change the information that you have encoded, then you should be able to go back by again another stimulus. So a little bit, the idea it is this. So if you take two constituents, and then one of the two constituents, for example, has a property, for example, fluorescence, and then at the beginning is fluorescent, then you react, you form an adduct that is not anymore fluorescent. And then if you want to have something that you can erase or you can change the properties, then what you should do, it is that you reverse the reaction upon a different stimulus, and then you go back to the initial fluorescence. So by making this multiple cycle, then you should have a fully writable system. You encode an information or you erase it. Now, if you now imagine that you could have this system organized in a material, and then you write specifically. So by writing specifically, it means that we do a reaction in a position, no? Then what we could be able, it is to create a matrix in which we have fluorescent, non-fluorescent, fluorescent, non-fluorescent. And then to the fluorescence, you give a signal, for example, 0 or 1. I mean, this depends only on the coding. And then to the other, the opposite. But of course, this is then you should be able also to erase and to go back to the initial state. Okay, how to do it? This is how to do it. And so the best among the different systems that we could use, for example, the formation of endoperoxide could be a simple reaction, a simple dynamic reaction that we could use to do this fluorescence on, fluorescence off. So if you take, for example, an anthracene, anthracene is very well known to undergo, in the presence of singlet oxygen, to form an endoperoxide. So if you take your anthracene, you react with a singlet oxygen, you form endoperoxide. But then by heating or by applying light, you could also do the opposite reaction, so the reverse reaction, for which you break the endoperoxide, you reform your anthracene, and then you eject a molecule of singlet oxygen, and then you restore the initial fluorescence. Okay, the problem it is what? That when you take only anthracene, anthracene cannot sensitize singlet oxygen, or the quantum yield of singlet oxygen sensitization is very bad. So what you need usually with anthracene, it is that you need to use a sensitizer which could generate singlet oxygen, and then this singlet oxygen react with the anthracene. Sorry? Ah, no, okay. And this is would not, or would be very difficult to put in a device, because in device we should put the anthracene, the sensitizer, and then the sensitizer should each time to prepare the singular oxygen upon a stimulus to react with the anthracene. So the best way would be now that if we take this anthracene, we extend the anthracene in such a way that the anthracene core with some functionality can become also a good triplet sensitizer upon excitation. Then what we could do that the singlet, the anthracene derivative could be also a singlet oxygen sensitizer. So essentially, the anthracene derivative should be able to sensitize the singlet oxygen, and then the singlet oxygen that has been self-sensitized by the anthracene derivative could react with the anthracene itself, forming the endoperoxide. And when you form the endoperoxide, the singlet oxygen sensitization is shot, and then it's finished. Only when you heat, you go back, you restore not only the fluorescence properties, but also the singlet oxygen sensitization properties. And then you can do this cycle n times. So how do we do it? So in the group, with the PX6, the molecule that I showed you before, we have a quite good experience on these Pirano rings. And then we know that anytime that you have a Pirano ring, type of Pirano ring, with this oxygen that is fused between aromatics, the molecule becomes a singlet oxygen sensitizer. And also a good one. Why? Because with this oxygen, favor some fluctuation in the molecule, for which then you favor some spin-orbit coupling. And so when you form a spin-orbit, when you have a molecule that has a good spin-orbit coupling, so then also you tend to favor the formation of the triplet excited states, which is also which is the one that sensitizes through triplet annihilation reaction the singlet oxygen. And so then we prepare this molecule that we figured out that also was known in the literature from the 80s to be also a good singlet oxygen sensitizer. And so we decide to prepare this molecule. So how do we prepare the molecule? It is quite straightforward. You start with this bromo derivative. You make the Grignard. So you add on the anthraquinone. the dichloroanthraquinone, then you reduce it, so you rearomatize, and then you deprotect this OH group, then you go nucleophilic aromatic substitution, and then you get in one pot the double oxygen bond. And then what we observe, this molecule is strong, is orangey. You can see here the color. This is, we got the crystal structure. So the molecule, it is slightly bended, which gives some distortion on the molecule, and so then it makes quite reactive. And then when you add, for example, singlet oxygen, and then you irradiate, you see that it becomes completely transparent. And so why this? Because of course here you break the conjugation, and then when you break the conjugation, you increase the homolumo, and then the molecule becomes transparent, because the only chromophoric unit are only these benzene rings which are not fully conjugated, and so that is completely transparent. And then we got also the crystal structure of this endoperoxide, which shows nicely the fact that we have the endoperoxide. Good. And then we started to study, can we use this as a system to store information? Is this dynamic reaction reversible? So this is what we did. So here we study the UV visible, and in particular the emission. So we look at the fluorescence, because these are the properties that we want. And so then what we did here, so we irradiate with a light at 450. So we form the singlet oxygen, which react with the molecule. And you see, in a few minutes, there is no more molecule. Then what we did, we heated. And then it took quite a while, but we could go back to the full concentration of the initial anthracene. And then essentially, we got all the initial molecule back after 300 minutes. And so here we have the kinetics. So we measure the kinetic of the system. And so what we see that it is very fast, the formation of the singlet oxygen, of the endoperoxide. And then what is nice, it is that when we compare the self-sensitized system, so we put only our molecules with oxygen and we check the kinetic of the endoperoxide, or we took a methylene blue, and then we did a sensitization reaction. So we excite the methylene blue that created the singlet oxygen, which then reacted with the endoperoxide. As you can see here, the kinetics is the same. So the molecule self-sensitization of the molecule is exactly the same in terms of speed as you would add an external sensitizer. The only thing is that after a while, it gets slower. And this is obvious, the reaction gets lower because you have less molecule in solution, because the molecule reacts with the singlet oxygen, and you decrease the concentration of the initial molecules that it was the self-sensitizer. Then instead, when you look at the back reaction, so at the reverse reaction, you see that here we are talking about the scale of a minute, and so that is much slower. Then we look also the kinetics in terms of dependence with the power of the lamp we use. And of course, it becomes a bit faster when you use lamp which are stronger in terms of power. And then we look at the fatigue. So this is a successive cycle of endoperoxide formation and then reverse reaction. And then you can see here that we don't lose much in solution. So the system is pretty stable. And so now what? Can we now add it in a real material? Can we write? And so then basically what we did, we took this molecule and we put it in a polymer. And then we spray coat on a glass. And so this is what we obtain. And so here, this is the color of the molecule on the glass in these polymers. And then we add a mask, and then we add LED, and we irradiate. So as you can see, depending on the shape of the mask, this is where we wrote, and here it was where it was covered by the mask. So you see, we can selectively induce the endoperoxide formation in some position. And then when you apply some some excitation light, you see that it's fluorescent. And then you put in the oven, 120 degrees, and then you completely erase, and then you go back fully to the initial system. Then we characterize, we know at the beginning in the polymer, the molecule is stable. Then we characterize here, and we see that we found the endoperoxide. Outside, it remains our molecule, and then we put it at the end. And then we see when we recover, we could get again our model. Then we could also print it, deposit on flexible substrate, and then write on PET. Very nice. But this is all microscopic. Can we go on the microscopic? Can we go really on data storage? And so then we collaborate here with the Austrian Academy of Science, with the quantum, the physics group, with Dr. Trupke, and then they have a system that they can write. So it is like a confocal microscope. So you put a laser, you excite in a position. So in this case, it is microscopic. And then with a camera, we read it. So this is how we do. So you write, and then what you do, you record the data. So where we apply the laser, this is our 1. Where we don't put the laser, this is our 0. And then you can do a scanning. And so essentially what you do, you could create your matrix. So this is what we did. So we could make small 1 micron dots. So to put one, this is only 1, 4, 3, 4, 5. And so you see, so all are the same. So we could increase the number of dots that we could write on the substrate. So when it is black here, kind of dark color, it means it's not emissive. Here it is emissive. So we could also write with the laser. So if you take this portion of the material, you write, you make the 3 hexagon. Again, those are at the micron level, and then you erase 70 degrees in minutes, and then you go back. So it is full erase. But now, can we store data? And this is, for example, this is what we did. We create this matrix. And then here we wrote these dots. And then if you take this as a 1, the other one, 1, where there is no writing is a 0, 1, 0. So we create this matrix. This is a binary system which corresponds to the symbol of the Austrian Academy of Science. And so how much can we write? So basically we could write 16 gigabit in 1 square inch. So what does it correspond? So some of you, at least those that are all like me, around the 50s, so I'm sure that they used the floppy disk. The floppy disk capacity was around 740. Then when I wrote my PhD, 4 years later, the DVD. So we are at 0.90 gigabit. And then you go with the DVD, 2.2, and now currently are the terabit store capacity, which are the USB memories, which are magnetic. So you see that with our system, that we can print on any surface. So you don't need particular care because you need the oxygen. You take any polymers, you put in there, you can write. So we got more or less, without optimization, a store capacity like a DVD. Now, in collaboration with them, what we are trying to do is to make this dot smaller. And if you are able to arrive at the nanometers level, so we are talking about 20 nanometers, then we can have the same storage capacity of a magnetic memory. Only that this we can write anywhere, even on simple surfaces. And so this is what we are trying to do. And also to replace the thermal back reaction with a photochemical induced. Okay, so this is, I finish my talk. But before to finish, I would like to thank all the people, first of all the funding agency, the University of Vienna and the European Union and the Austrian National Foundation and for applied and for fundamental science, and then my research group that has changed. Now the picture is quite old, but we are around 2025 working the group. And then also we are always looking for motivated students, PhD and postdoc. And so if there are any interest from you, feel free to apply to our group. And again, thanks you all for your kind attention and the invitation to be here today. Thank you.
Thank you very much for your nice and very interesting presentation. Dear colleagues, do you have any questions to our lecture? I don't see.
Maybe I have one small question. May I?
Yes, of course.
Thank you, Davide, for very interesting lecture with a lot of impressive results. And I have a small question out of my curiosity. When you told us about the first approach to the target molecules, you said that one of the obtained compounds generated singlet oxygen, yes?
Which
In
one?
the beginning.
The boron?
Yes, yes. When you told us about the first approach to the... Yes, and did you
Which
think
one?
about... have you ever thought about biomedical applications of these materials? Maybe for antibacterial photodynamic therapy?
No, because I mean, as you know, I'm in the bio. We have some research in the bio, but I'm not really in the field. No, we did not do it. Also because some of these molecules are quite complicated for the synthesis, so there are molecules which are probably easier to be prepared and to get nice singlet oxygen sensitization. What I can say it is that I've been asked to use this molecule. So the molecule that I show here, this has been contacted by a couple of people, and they asked me whether we could make this molecule soluble in water. And could be a good transporter of singlet oxygen, because what you could attach to this molecule a tag, which brings then to the position that it should be brought. And then by applying a little bit of heat, you could be able to regenerate the singlet oxygen, which then oxidizes it. Okay? Because when you do the cyclo-reversion reaction, you produce singlet oxygen. And so what I've been asked to see whether we could make them soluble in water, and so as a singlet oxygen carrier.
Okay, sounds interesting. Thank you.
Thank you very much. Somebody else? Okay, I have a general question about competition between organic and inorganic materials for data storage. What do you think? Is it possible for organic compounds, for organic materials to win these competitions with inorganic? And what about real application of organic compounds for data storage? Because density capacity is not very high at the moment.
Sorry, no, as I show also, all the semiconductor is based on silicon and inorganic. So at the moment, the organic is a niche. What I can say that the inorganic has the advantage that you can tailor the properties as you want, and then you can integrate them in flexible systems. Okay, so this is, and in terms of processability, it's enough that they are soluble. You can spray coat. I mean, are very easy. The problem, usually it comes with the resistance, the thermal resilience, the chemical resilience. This is the big problem that we need to face. Organic molecules are used in nature as a semiconductor, but nature, each summer, at the end of the summer, they replace the leaf for the next season. And so there is a constant regeneration of this chromophore, something that we cannot do. So the only way it is to make them more robust. And I think if we are able to find a structure in which we use an insulating, when I say insulating, it's thermal, electric, and also chemical, like protection. And then you are able to keep the core of the organic molecule protected, then it may have a home. But until we don't reach that, the inorganic, for these characteristics of being so stable towards light, towards oxygen, of course, then they will always win.
Yeah, I think
this is gonna
I think it's the same manner. Yeah, okay. And other question, joking question, what's the difference between two insoluble molecules and insoluble molecules? You had both of these.
Yes, no, one molecule we could not, I mean, one molecule we could not even, we got a mass, that's it. We could not get NMR, we could not get anything, really nothing. The other molecule, we could get easily the mass, and then now we have also NMR, but we had to do very diluted condition, and we could see a little bit the NMR. But for example, we could not record the carbon because the concentration was not enough. But fortunately, we could get the crystal. And so now with the crystal, we prove that we have the molecule. So yeah, it is more a qualitative one that is a rock. The other one, at least we could run an NMR.
Yeah. Okay. And other question, you have a target compound, insoluble target compound, and maybe you also have a lot of impurities, maybe also insoluble. What about purification of your target compounds from other insoluble molecules?
So now what we do, I mean, when they are very, very insoluble, usually then what we need to do, it is, okay, beside the mass, we need to do another reaction after to make them soluble. Okay, so because otherwise we cannot. For the purification, it depends. We can use Soxhlet extraction. Okay, so this is when they are very impure, like with polymers. You know, you make this Soxhlet extraction, which allows you to make them pure. Or we go with high temperature crystallization. So we use high boiling point solvent. We try to go as much as high in temperature to be able at least to slightly dissolve, and then we co-crystallize. And then we crystallize. And so then usually, then we can get good crystal, and so we pick the crystals, and then we characterize the crystals. And this is, for example, what we did for one of the molecules that we could get only NMR. So we take the single crystals, also for the characterization.
Okay, thank you. So dear colleagues, do you have some questions or maybe comments? Nobody. Okay. Dear Davide, thank you again for your very interesting and educational maybe lecture concerning such interesting, not only chemistry, but material science. Thank you for your agreement to be our lecturer on Kharkiv Chemical Seminar. It's very important for us.
Yeah, it was a pleasure. Pleasure was all mine.
Thanks, and have a nice day.
Thank you. Bye-bye.
Bye, Olesya. Bye, Valentin.
See you.
Thank you.